Master of Learning. So I am Cyril Pisakovich from Physiological. I started my way in Russia as a mathematician in Novosibirsk State University. Good like this. Don't move. Okay. And then I went to France to get my aerospace engineering degree in École Polytechnique and des Supérieurs in aerospace system and automatic control. I did my PhD mostly on pupil diameter analysis, visualization of eye movement gazes, and a bit of work on eye movements. So now I'm at the Superior at Human Factors Lab. So you're all welcome to come to Toulouse to discover what we do at the campus. This is our lab. We co-founded a startup with my colleagues called InFact 2018. It's about providing solutions for flight instructors and the air companies. So you can check out the website. And now I'm associate professor in human factors and human spaceflight. We have 9 aircraft, so we do stuff in flight. I am learning how to fly the aircraft. We have flight simulators, and we are starting to do a job underwater to try to do physiological monitoring underwater. I will be talking about it a bit later. So why human factors matters in aerospace? In general, I'll start with I'll start with a small accident with 1974. So it's American station Skylab. It's last mission. They did only 4 missions to the station. They going back and they mistakenly pulled the wrong breakers. So instead of deactivating propulsion, they deactivated orientation. So they couldn't orient properly and automatically the heat shield. Eventually they switched to manual mode. Everything went fine, but small human mistake would lead to catastrophic events. So that's because of high workload, the G forces and all that heat that you experience. So things can go not as you foreseen. Another example from commercial spaceflight, 2014, Virgin Galactic Spaceship 2 that ended up quite badly. It's an example of how new space and new actors in sectors they should apply the same safety margins, let's say, as classical players, as state agencies. So they needed to deploy this feather mechanism that supposed to increase drag to enter the atmosphere, and they deployed it in the wrong moment. So the NTSB report found especially that the training wasn't enough. There were faulty designs that one action could result in such a catastrophic event. And also they did have a simulator, but they never expected to try to test this stuff in highly vibrant and highly noisy with lots of acceleration. So the procedures they trained on the ground were not quite representative of what they did actually in space, in suborbital space. Another small example from 2021. So it's Nauka module. It's the lightest that docked to the International Space Station. It's the exact twin of the very first ESS module. So it waited on Earth for 20 years. The moment was quite emotional for especially the Russian space sector. The docking it lasted for 9-10 days. So it was the approaching. It was quite an emotional moment. And if you remember, the station started spinning. So they eventually gained the control. And apparently, because of some interview in Russian Cosmos journal, one of the controllers forgot to deactivate the propulsion system upon docking. So something the procedure supposed to do. Because of this euphoria, actually, in the control center, because they waited for a long time, finally they got it here, and so they just omit one simple action. Eventually, everything went fine, but emotions also and all this. Space is hard. There are lots of people involved, and in such moments, you can be kind of submerged by other things than just procedural training. So a few more examples from not from spaceflight, but from commercial aviation. Lots of things happen every day, starting from one of the first human factors examples in 1972. So it's just a crash in Everglades. It was a high-tech aircraft for the time, and the pilots, they were starting to deploy the landing gear, and the middle green light you can see on the picture, it wasn't on. So they didn't know whether the light bulb was faulty or the landing gear wasn't out. So not the same problem. So actually they were 4 at the moment. Nowadays we have two people crew. At the time they were 4. They spent 15 minutes trying to change the light bulb, so they were completely distracted. They never monitored the descent path, and eventually they ended quite bad. Another example, they misunderstood the automatic go-round initiated by aircraft, so they spent lots of time as well without noticing it. They noticed eventually overspeed and overslope. They tried to reduce the thrust, and on the runway, one of the thrusters, it slipped forward, so they ended up in runway excursion. They ended up quite fine, but it's also the incomprehension of aircraft function and crew that can be a challenge as well. So there are lots of examples like that. Not very human factors example, but put here anyway. So Rio Paris, quite catastrophic event, stall in cruise phase. So because of the iced fighter tubes, there one of the problems were not enough intent verbalization by pilots, so they didn't communicate quite well. Also because the phase is quite low, normally the higher cognitive load phases are landing and takeoff, for example. So in cruise, normally everything is fine. You can talk freely, you can drink coffee as you want, eat, etc. So because of this moment, which is not supposed to be high difficulty, high workload, they were not kind of operating the same way they would during landing, for example. A few more recent examples as well. So post-COVID maintenance problems, they forgot to remove the cache. So lost redundancy of altitude and speed indications in flight. This is a stability approach. So you can see the impact. It's a 4G hard landing. Most problems nowadays are in stabilized approach. So you arrive too quickly to you're a bit far beyond the slope, and at the last moment you try to land. So it's very costly for the maintenance, for the landing gear as well. And that often happens because you don't monitor properly your speed or your slope, your altitude, your vertical speed. So all the parameters are there. Another fun example from quite recently in Indonesia, one pilot went to sleep. He asks his co-pilot to kind of be there and stay with him. He also was tired, so both pilots were asleep at the time. Eventually, everything went fine. But this is something that happens all the time. So problems with inattention, distraction, fatigue, overload, all this, it's not just something from research, it's something that happens there. Mostly nothing happens, everything went fine. But in some cases, there are accidents and incidents, so we need to properly monitor that. And just one last example from the space. So you can see it's a small quiz that allows me to breathe a bit. So they put in the EVA suit. I'll accelerate a bit the video. So it's 1997. It's Mirror Station, and they put in the EVA suit. Sorry. But they're not going out. They'll be working inside the station. So it's normally it's not what should be done, but it was being there because of a depressurization of one of the modules. It was Mir Progress accident in 1997. They had quite bad year in 97 at the Mir station. They had fire previously in the summer. Later, they tried to actually test manual docking versus automatic docking for the Progress cargo vehicle because they wanted to spend less fuel for the docking, so they thought manual could work better. Then the control center pressured the cosmonauts on orbit to perform it. Cosmonauts actually were quite resistant, but also the hierarchy plays a role. So they said, we are tired, we're not feeling it, let's train more. But ground control insisted, so they performed it. There was one docking that ended quite almost in an accident. Ground control asked for one more. And eventually, so they disconnected the automatic one. They tried to do it in manual mode. They had only this old video screen to perform it. And actually the progress, it hit the mirror, the spectral module, just a few meters per second more than it was supposed to. So it actually punctured the solar panels, it punctured the module. So it's still, they tried to repair it for a few years, but till the very last days of the mirror station, there was a small leak because of that accident. So it also shows that this human factor sits on all the stages. You know, the Swiss cheese model, which is normally was invented for nuclear plants. There is a version which called HVACs for the aerospace. It shows that often when we think about human error and human problems, we think about the last chain, so operator, cosmonaut, pilot. There are lots of layers of that. So unsafe acts, they're often preceded by some preconditions for unsafe acts. Then supervisory factors and organizational influences. It's not often evident to go to the upper layers. So what we see at the end of the chain, unsafe acts, for example, pilot, he went to sleep. But why he went to sleep? Well, because he was very tired. Why he was very tired? Because his company didn't have enough pilots to recruit them. So they made his shift so tight that he didn't get enough rest. Why is that? Because maybe they didn't get enough money. So, you know, all this chain, it's not actually the pilot's fault. We are all human. We have our kind of limitations of attention, cognition, physical, etc., etc. So human factors are involved in all these steps. And so we are all kind of human. This is a human spaceflight. It's an example of complex social technical system. All the people who are doctors, who design suits, who design aircraft, ground control operators. So all this can happen at each stage. So a bit of physiological monitoring out of the lab. It started a century ago, let's say, with Net and students in Germany. So they started to study actually the metabolism of people in high altitude conditions, but they didn't have at the time the capacity to do that out of the lab. So they tried to invent before that to study the metabolism and how much of CO2 and oxygen you get. So they did the chambers like this. Then they invented kind of a more light stationary device where you can lie down and it will be not in such closed room. And then they invent also a portable, what today will be called a wearable. You can see it also was kind of low budget. It's an inverted chair they have on the back. So it's a portable device. You can see also kind of speed of the wind measurements. They had also this metrics of mechanical detection of the pulse and heart rate, for example. So it started, so they said, okay, we cannot actually reproduce the high mountain conditions in the lab. So we need actually to get out there and to study physiology in real conditions out of the lab. So we need to innovate. We need to do this out of the lab, do in real operational conditions. That's a bit about of space exploration. So the physiology, it was a kind of main part of it as well, because of mostly health. So starting from animal factor, so Gulliver and Bonnie, the first long stay missions in space, they had multiple of sensors, all the electrophysiology we know today, so all this blood pressure and EEG, ECG and all that. Actually, Bonnie, for example, he's supposed to fly there in 30 days, but he ended up only flying 9 because he got sick of all these sensors. So they aborted the mission. So they had much more channels than they needed to, but it was the first ever exploration. The same goes for human spaceflight. So starting from Vostok mission, where they, of course, this is like a historical artifact of, if you can read the date, so it's 11 April 61. So the ECG and blood pressure of Gagarin to see if he's in good health. They did it from the first space station, from Salyut station. So they already has all this medical equipment to see if people are in good health. In neural labs, they get in mirror station a bit of more sophisticated, etc., etc. From lunar hot as well for teleoperation. So that nice nice literature. It's not very traduced in English, but it was nice to read. So actually, because they were very scared of losing the lunar hot 1, they needed to operate continuously for 14 days for the lunar days. So they had crews that were selected for the same level as normal cosmonauts, aside from G-forces, from centrifuge exercise. They had 2 crews of 4 people who were working 2 hours, shifts by 2 hours, non-stop for 14 days, then 14 days rest, and they worked in that regime for 1 year. And each one of them had 1 medical doctor assigned to them that were tracing their vitals in kind of real time because they were so scared to lose this device. So even in teleoperation, so nowadays ground operators are not monitored with that kind of rigor, but from the first operation, people said, okay, like we need to be in good health, of course. And actually nowadays we can easily measure lots of stuff. I'll just go yes, a bit of that. So this is mostly what we use in our laboratory. So brain activity can be measured either electronically, so e.g. electroencephalography, the electrical potential on the skull. We can do FNIRS, functional near-infrared spectroscopy, so you see the oxygenation of the brain, so you get hemodynamic response. It's a little bit slower, but it's still good. We can do it in space. We can measure face temperature as well, which is a nice indicator of workload as well. As the workload gets high, our forehead gets a bit hotter, our nose gets a bit colder. We can use ion gaze tracking. I'll have a slide about that a bit later. ECG electrocardiography, which is very low cost and small form factor nowadays. Electromyography, for example, EMG, when pilots they grasp to the thrust levels, for example, we can now detect that. And all that should be put into the kind of system state context. So what is the flight phase, what is the automation is around, etc., etc. So nowadays, yeah, we can mostly, so this is all the pics from our lab. We can fly almost everything, e.g. NIRS, eye tracking, gaze tracking. So the devices, they are smaller, they're more portable, they're battery dependent, they're a bit more complex to process because of the artifacts, of course. But it's feasible, it's there. So it's not kind of science fiction anymore. We can do it. Mostly of that also flew already in space or distant parabolic flights. I think the latest was the FNIRS, but in one of the Axiom last missions, I think they still got it on in space as well. So in spaceflight, there is also this kind of in human factors part, what's called health performance continuum. So it means that you want to be good at your task, but also in good health. So you want to have perfect health, perfect performance. Sometimes you have perfect health, but poor performance because of some other factors. Then you can apply countermeasures for performance related. Sometimes you have still good performance because you compensate for your poor health because you have some health issues. Then the countermeasures will be health related. So they're codependent kind of. And mostly of the physiology that happened today in space and is still there. So it's health related. In research domain, it's still performance related. But in operational settings, it's health related. For example, during EVA, they monitor the vitals in real time. In ground control, they see at least heart rate and blood pressure. But it's not for performance, it's just to see if they're well enough. So health is already operational. There are lots of research going on how to estimate task performance based on your physiology. And in a few years, it will be, or it should be at least operational in aerospace as well. So I skip this a bit. So this is for eye tracking. Just to say that kind of we want to monitor our eye gaze. The idea is not new. It's just that the technology went more forward. So it's the same. It's an extract from NASA paper from 60s or 50s maybe. So the idea is that you show the gaze pattern. You can see it here to the instructor of your flight training. Nowadays we can do the same thing in a full flight simulator on an iPad of both pilots in real time, higher frequency, lower times of data analysis. So the idea is exactly the same, but the just eye tracking technology got better. So now we can do it in real time without any issues. So a few in-flight examples of eye tracking in particular, also from what Pradipta Biswas did here. So we can compute lots of stuff in real time. We want to estimate some states of pilots, starting from basic cockpit visual scanning, how much time I spent on that or that instrument, how many seconds did I not monitor the speed, for example, go into more complex states such as fatigue sleep, hypoxia, for example, spatial disorientation. So it's a bit more complex, lots of variability between participants, but it's still feasible. So also the integration of these devices nowadays quite feasible. So this is an example of what we did with, in fact, at INAC, French Aviation Civil University, that form pilots. So they're behind eye tracking works in infrared domain, so you can hide them between small visible light filters. So it's feasible. You can retrofit flight simulators. Roughly, the main problem is the cost for the companies, because they're not still used to it, so they're not ready to pay directly this sum to retrofit all their simulators, because the monetary gain, it's not obvious for them, but it's obvious for people who work on human factors. In real aircraft, it's also possible to integrate. So we have, this is one of our aircraft, twin engine P68. So we have two cameras there and scene camera, so we can see the flight gaze. The eye gaze, it's real time, it's streamed on your computer. You can do it in flight, so all the flight deck is simulated. So it works with sunglasses. So it's feasible today. It's just the matter of kind of time, cost, a bit of certification, so a bit of paperwork as well. We integrated kind of above the flight deck, not behind, not to modify too much. For certification purposes, but I mean, it's feasible. It's just a question of kind of goodwill of people and a bit of monetary inversion. So I want to finish with a few examples of research projects and an example of an industrial project. So this is from Teleop that we've tried to understand. So it's one of the PhD thesis we started to funded by CNAS and ESA. Nowadays, we can teleoperate stuff from mobile platforms, so from boats, moving vehicles, aircraft, helicopters. For example, there are helicopters for mountain rescue missions that have the body drone, that they have the visual feed in helicopter. The problem with this is that often we can have visual vestibular conflicts, but mostly we are in the same, we see the same environment that we are in. When you teleoperate this thing, you can visual vestibular conflict because of these different kind of places. Okay, so you're in one place, the visual that you get is the other. So vestibular and visuals, they get the kind of signal from different places. So actually, first we use this chair to prove that if you are going to the left, for example, and you need to operate your vehicle to the right, you'll be slower and less accurate. So there is kind of this conflict of vestibular and visuals, even if visuals they come from remote operations. We established it first in the lab. Then we started to do it in flight. So we were doing the G-turn, so 30 and 60 degrees. At 60 degrees, you get 2 Gs, and 30 degrees, you get 1.4 G. They did the same task they did in the lab. We had some other problems of setting this up with security margins. But we actually, the fun part was that we did find the subjective results. So the people, they kind of suffered 2 Gs because they're not used too much for this kind of turns. We did subjective results, yes, but we didn't get the objective results. So they maintained their performance, even if they were kind of overloaded subjectively. It was our first study, so we didn't measure any physiology for that yet, because we kind of wanted just to set up the research protocol properly. And it shows that, so in sometimes most humans do, they can kind of compensate for more difficult tasks by just applying more resources. And if you're not on the limit, so if you don't apply some physiology measurements, you don't know that. So same performance doesn't mean the same resources allocated to the task. So that's one example of what you want to actually do some physiological measurements to see, okay, you have same performance, but did it cost you more? So another example from real simulated flight, we compared flight simulators, real flight, and more conventional flight simulators. This one is with virtual reality. So we saw that within the flight, different flight phases, they induced different responses. So this is heart rate and fixation numbers. So low fixation numbers means you're more focused on the task, more focused on the one point. So we saw that while within the flight, all the simulators, they kind of reproduced different difficulties of flight phases between modalities. Still, real life, it elicited high response. And so even if everything is fine in virtual, you still need to go to do the real operations because it's not the same physiologically. So it might be the same in terms of performance or subjective estimation, but your physiology, your heart, and your brain, your eyes, they could tell the difference. So yeah, I'll skip this. So this is my examples as well of trying to innovate a bit in physiological devices. So we used very simple, out-of-the-box kind of low-cost open BCI device to measure potential around the ears and around the nose. So the idea is that normally you have some kind of gear around your headset, for example. For the fighter pilots, you have the space to integrate some electrodes around the nose. So we want to see if it was feasible. So we did some centrifuge testing as well for that. Because for this, we use the dry electrode. So it's not, you don't add some gel. It's a kind of just silver coated dry electrodes. They can be quite uncomfortable. So we stand them up to 4Gs. And one of why you need to go out of the lab and try things we didn't expect. So this, you can see the small deflections of the signals. This is saccades and blinks with the measurements of difference potential here between 2 years. And while increasing the Gs, actually, we were able to measure it up to 2Gs. But later, the blood started to pump so much that we got only artifacts from the veins here. So we were able to measure the heart rate normally, but it kind of disappeared, made disappear the blinks and the saccades. So we didn't expect to have this kind of signals at 3/4. So this, you need to go out of the lab to see it really. Another example from the in-flights. So the pilot performed the small patterns. We could see if we could get saccades, horizontal, vertical, and blinks. You could see the blinks, the small deflections. The signal is quite noisy. This is just one example. We had the footage, so we could see it. Sometimes in some loops, for example, they have the sound scene phase. So something we didn't foresee. We thought, okay, it will be saccade, 3 blinks. Could we search for that info in the data? And then we saw much more blinks that we expected. We saw the raw footage, and we see that actually it was real blinking coming from the sun. But here the message is that it's kind of feasible, only 2 points here, and you can sell with very low cost, easy to deploy tech in very high demand conditions. So they performed up to 4Gs, 5 different loops and loopings, and even the thing you can see on the right, so called read. So in all these demanding conditions, you can still measure physiology, at least some simple parts of it. Another thing we did just last month, so it's at ESA, the lunar facility. We did FNIRS and ECG recording of people that were trying to navigate a small rover. So the difficulty of task was different task difficulty, flat surface navigation, and then deep floor area obstacle avoidance navigation. And they were in 2 conditions. One was kind of control condition. They wear all the gear aside the face respiratory mask, and the lights were on. In another setting, the lights were off, and they had the full gear to protect them from the dust. So it's affected not the task difficulty, but the kind of environment. It's affected both heart rate and HBO changes, so the FNIRS, the brain oxygenation, but it didn't affect their performance. So another example that the environment can affect just your physiology. You can maintain the performance well at the same level, but just this turning off the light and having something more on your head can affect how your body reacts to that. Last example of research project. So what we're doing right now, it's trying to go underwater as well. So the problem of monitoring diving activity is that if you wear a dry suit, most of the things you can wear on your body, it can work underwater. It's not the same for the head. So nowadays we are trying to use this suction electrodes on your forehead, actually, to make this compatible with the scuba diving. So it's still underwater. It's still undergoing. But we are trying to design the same system with kind of low cost data processing. Mostly the part is the suction and how to not get too much suction to get the hematoma. So we are trying to work on that. I'll skip this. No, okay, I'll show this. So just to show this was one of the trainings we were doing. It's just a small message for the why it's interesting as a researcher to go out and test all this stuff as well. So we were diving. It was quite long, quite cold. So 10 degrees, 10 meters, roughly 11 degrees. So you're kind of freezing. You're a bit, if you think, so I kind of think of myself as above average intelligence, but when you put into this stuff, you kind of become a bit stupid as well. And it's interesting to experience all these things. So just at some minutes, you understand that you're just breathing, you're fixating one point, you're useless, you're just there, and you understand, okay, maybe it's interesting to have physiology, because even if you're you think, okay, it would never happen to me, right? I am can handle this kind of task. Apparently not always, so it's interesting to get out, to experience what you actually study, to feel this, to live this, so to become a better researcher. So to wrap up, human factors still are critical in our space operations, still to our days. There are lots of physiological monitoring devices that are now available for out of the lab measurements. So, or you can build some. The components are available as well. Monitorings matter, and now we have objective tools that can be integrated. So eye tracking in particular, it went from kind of promising to proven, and you can integrate it in your flight simulators or real aircraft. There are still lots of research questions, of course, for complex mental states, complex physiological states, but there are lots of many out-of-the-box algorithms that can get you. So one of the earliest, for example, the fatigue devices. Nowadays in automotive, there are lots of algorithms to estimate your fatigue state, and there are around 1 million cars already, I think, mostly in China and in Scandinavia, but there are lots of cars with integrated eye tracking, estimated fatigue state that works, that are kind of proven. So in a few years, it should be in aerospace as well. So we want to try to get as possible to the real operational conditions, because it's quite difficult from the lab. So often you get lots of surprises you haven't foreseen at all. So it's fun and it's useful for science. And so let's track your physiological parameters to have perfect health, but also good operational conditions, and get it kind of there to the world. So thank you. Good. If you have any questions, maybe